All right, so today is Monday, April 27th, and we're going to, and it says inferences for sample means. Wonderful. That's not what we're doing. We're doing inferences for sample proportions. Not sure where I made that change, but apparently I didn't save that change or I did it. Anyway, but it's inferences for sample proportions. You'll see that it's 174 to 200 in your notes, but then it also says pages 147 to 156. Pages 147 to 156 focus primarily on type 1 and type 2 errors, which we'll be talking about a little bit today and then a fair amount on Friday. 174 to 200 is basically going to be your 1 and 2 sample proportion, hypothesis test, and confidence interval. Today we're going to skim very, very rapidly through some notes, and then we're going to do about 4 FRQ problems, and then we'll plan on doing 4 on Wednesday and another 4 on Friday. Okay, so a couple things. As I've said before, review your note spiral. Tab all your recipes. That said, I'm going to try to get something up on the website, not this week, but next week. That would be a really quick, could be a quick reference for you, but that hasn't been done. So it'd be sometime next week where you can quickly find things. And the reason I'm doing that is because you're allowed to have access to it during the AP exam. So anything that I can do to help you guys out, I will do within reason, as long as it's honest. And then, and if you have suggestions, I mean, I can tell you what I think will help you, but you need to let me know of ideas, and I'll give you an opportunity at the end of today's lesson to give some, or you can email me some at your own leisure. All right, so one sample confidence intervals for proportions. First off, this is the formula. The great thing is you don't have to memorize the formula this year. It will be, it'll be available to you. If you're going to use Q hat, you need to make sure that you say what Q hat is, and Q hat is just 1 minus P. If you choose not to do that, you can do P hat plus or minus Z star, P hat times 1 minus P hat all over N. So one of these two formulas, but if you use this one, which is my preference, you're going to need to show Q, what Q is. Please remember, P hat equals X over N. X is the number of successes, or what we're interested in. N is the number, is the sample size. Please remember, X and N must be whole numbers. Last year, that caused someone a problem because they didn't remember that. They went to run the test on the AP exam. They used a decimal for X, and they just needed to round, and consequently, the calculator kept saying error because it will not accept it. So X and N must be whole numbers. Your conditions are simple random sample. That should be given to you. You need to make sure that you say simple random sample, and then you need to say it's given in the question stem. N is less than 10% of the population, or N divided by 0.1. The purpose is because we were sampling out without replacement. This condition ensures that the observations are independent enough, or the degree of dependence is small. Please remember, we talked about the giant pile of M&Ms, and I keep going back to that because hopefully it'll stick. That we had, I go and I take one red M&M. Consequently, the proportion of red M&Ms changed, but it only changed slightly. So as long as it's less than 10% of the sample is less than 10%, we don't worry about it. Then we have NP and NQ both need to be greater than 10. Of course, if you use Q, you're going to have to say Q is 1 minus P up here, but if you say it once, it counts for the entire problem. Otherwise, right here, you're going to need to write N times 1 minus P hat. All right? Those need to be greater than 10, and the reason they need to be greater than 10 is it ensures that our sample is large enough for the distribution of sampling proportions to be approximately normal. All right? And so that's the reason for that. I would make sure you know the reasons. They might ask you. You don't have, unless they do ask you, you do not have to explain why. Same with here, same with this. I wouldn't know why, but just in case they ask, but it is, otherwise, you don't need to write it. Width of the interval. The width of the interval gets wider as the confidence level increases. So if we go from 90 to 95%, my interval gets wider. Why? Because my z-star increases. If we had a 90% interval, my z-star would be 1.645, but with a 95%, it's 1.96. Obviously, 1.96 is bigger, so if I'm multiplying by a bigger number, it's going to get wider. As n gets smaller, my interval gets wider. All right? And then lastly, the confusing one. As my p hat gets closer to 0.5, the closer it is to 0.5, the wider it is. When it's at 0.5, it is as wide as it possibly can be. All right? So at 0.5, that's the widest, that makes this part as large as it possibly can, this numerator. Decreases is just the opposite direction, so I don't need to really talk about that. One sample hypothesis test for proportions. Here's our formula. Once again, p hat minus p naught, and then p naught times q naught. Please make sure that if you use q, that you define it. Make sure you do that. If you'll notice here, the standard error, this part right here, that's the standard error, uses p naught instead of p hat. And there's a reason for this, because in this case, we've made a claim because we're running a hypothesis test. So our claim is going to be the null hypothesis, p equals something. And whatever we say p equals is going to go here. Up here, when we did a confidence interval, we didn't know. We were trying to make an estimate for p, and since we're trying to make an estimate for it, we had to use from the sample. So this is why we're using the sample. By the way, I should have said this already. This part right here is known as the margin of error. And this part without the z is the standard error. All right? Okay. Our conditions are exactly the same as we had before. So simple random sample, n is less than 10% of the population. And then, of course, NP and NQ must both be greater than 10. So those are the conditions are the same. The standard, the conditions are the same for one sample proportion and one sample hypothesis test. The only real difference is in the standard error, okay? All right, p-value. P-value, first off, it is a conditional probability, and it tells you that the random chance probability of getting a test statistic as extreme or more extreme given the null is true. So you ran a test, you got a probability, what's the likelihood you'd get a test statistic that extreme or more extreme given the null hypothesis is true. Make sure you always put it in context. And then one last note, the p-value is not the probability that the null hypothesis is true. So it's really important that you put things in context. I highly recommend that if they ask you the p-value, you say the chance of getting a test statistic that's extreme or more, given the null is true, then put it in context, and that should always get you full credit if you were to do that. Then we have a two-sample confidence interval for proportions. Boy, that was difficult to say. A two-sample confidence interval for proportions. And we're just finding the difference in proportions. And once again, if you're using Q hats, you have to say Q hat is 1 minus P hat. Make sure you do that. Our conditions are the same, except we need to do it for both of them. And we need to say that the samples are independent. This is really key. You go ahead and say we have two independent random samples. Whereas before it was just a random sample, now we have two independent random samples. And make sure you include the word independent. You need to do n is less than 10% for both samples, and you need to check that it's large enough for both samples. Then we get to the more difficult problem, which is the two-sample hypothesis test for proportion. Because here we're no longer using P naught, and this p hat is not x over n. It is the combination of my successes for both samples. And there's a reason why this is done. And it's because the null hypothesis is essentially P1 equals P2. So if we assume that to be true, that means that these two proportions, if combined together, would give me a better estimate. So consequently, I combine the successes for each and the sample sizes for each in order to get my P hat C, and this is, of course, 1 minus that, and P hat C and 1 minus that. Type 1 and type 2 errors. Type 1 error is, again, it's a conditional probability. It's measured by alpha. So if you have an alpha of 0.05, you're saying, hey, you know what? I'm fine being wrong 5% of the time. Definition: the probability of rejecting the null given the null is true. Simplified definition: rejecting a true null and accepting a false alternative. Doesn't matter which one you use of those, but if they ask you for a type 1 error, give them a definition. It could be the straight up definition, the more correct definition, or the simplified. Either one is fine. Then put it in context. All right, always put it in context. And I highly recommend you provide an additional consequence in simplified language. So don't only put it in context, but also provide the consequence of making that error, and do so in simplified language. Type 2 error is a conditional probability. It's measured by beta. And a type 2, and I don't know why, but for some reason this is an issue for some people. Type 2 is fail to reject. So type 2, fail to, maybe that'll help people remember. The probability of failing to reject a null given the null is false, or failing to reject a false null. Make sure you always include it in context, and make sure you always provide a consequence in simplified language. It's really important that you provide that consequence in simplified language. Once again, another conditional probability, it's power. Now, type 1 and type 2 are errors. Power is actually doing the correct thing. It's the probability of correctly rejecting a false null. It's a correct decision. Alternatively, we could say that power is a probability of rejecting a null given that it is false. We can increase power of the test by increasing sample size. There's a direct relationship between power and type 1 error. As power increases, the probability of a type 1 error increases. If we increase our alpha level, our power goes up because it's easier to reject. There's an inverse relationship between power and type 2. As power increases, the probability of a type 2 error decreases. And power equals 1 minus beta. So if they give you type 2 error, you can figure out power. If they give you power, you can figure out type 2 error. There's no other good way to do that. Okay. So, told you we'd skim through some notes very, very rapidly and then get to questions. So problem 1. A humane society wanted to estimate with 95% confidence the proportion of households in its county that owns at least one dog. Interpret the 95% confidence level. So here they're not saying confidence interval, they're saying confidence level. And so this is where we get to say, in repeated sampling, we'd expect that on average, our method would capture the true population proportions of households that own at least one dog 95% of the time. If you did that, that's full credit. And that's all that had to be done. That's in context, and it also shows knowledge of the question. Make sure everything you do is in context. Part B, the Humane Society selected a random sample of households in its county and used the sample to estimate the proportion of all households that own at least one dog. The conditions for calculating a 95% confidence interval for the proportion of households in this county that own at least one dog were checked and verified, and the resulting confidence interval was 0.417 plus or minus 0.119. Okay. A National Pet Products Association claimed that 39% of all households owned at least one dog. Does the Humane Society's interval estimate provide evidence that the proportion of dog owners is different from the claimed national proportion? Well, so first off, what I did is I took 0.417 and subtracted the margin of error, and I got 0.298. Then I took the proportion and added the margin of error and got 0.536, and this gave me my interval. So that's my interval. And what can I say about that interval? Well, I'm 95% confident that the true population proportion of households that own at least one dog lies within this interval. Because 0.39 lies within the interval, we do not have sufficient evidence to suggest at the 95% confidence level that the proportion of households that own at least one dog is different than the Humane Society's claim. So there is no difference because it lies within the interval, or we can't tell of a difference. Then the next question was, how many households were selected in the Humane Society sample? Show how you obtained your work. Well, first off, I need to sit there and go, what do I know about this? One, I know the formula. All right, that's the formula for confidence interval. They tell me it's a 95% confidence interval. And they also gave me the center, or their estimate of 0.417. So remembering this part of it represents the margin of error, I rewrote it, and then I started plugging in. So the margin of error is 0.119. If I do a second VAR's inverse norm of 1.9, if I do a second VAR's, I should go ahead and do that. So then just say it, I should go ahead and do it. Second VAR's inverse norm, parenthesis 1 minus 0.95 divided by 2. Oops. Twice in a row I hit the wrong button. Try again. There we go. And so I get 1.96. Obviously this is negative, but I always make that positive. Please always do that. I divided both sides by 1.96. I squared it so that the radical came off. I divided, and I ended up getting 65.95. So n equals 66, so the Humane Society must have selected 66 households. Now in this case, it's obvious that you'd round up because you normally round up in this case. But even if this had been 65.1, always round up when you're working with sample size. Please make sure you do that. Please make sure you give your calculator value, whatever you calculated, and then show that you're rounding. They need to see both. Okay? Please make sure you do that. Anyway, that was problem 1 for 2010. Not too bad. A little longer problem, but still pretty straightforward as far as I'm concerned. But it's been a while since we've done this. 2011, Form B, question 5. During a flu vaccine shortage in the United States, sounds like coronavirus, it was believed that 45% of vaccine eligible people received a flu vaccine, except we don't have one right now for coronavirus. The result of a survey given to a random sample of 2,350 vaccine eligible people indicated that 978 of the 2,350 received the vaccine. So this right here would be my X value. This right here would be my N for P hat equals X over N. So that's where that's going to come from. As always, I define my parameter. My parameter is P. Let P equal the true population proportion of vaccine eligible people who received the vaccine. I write my formula. I make sure I write Q as 1 minus P. We have simple random sample of 2,350, and that was given. N is less than 10% of the population, 2,350 divided by 0.1. There's at least 2,350 people eligible for a vaccine in the US. in P. This time, since they gave me my number of successes, I could just write it down, and 938 is greater than or equal to 10. I can check that off. And then 2,350, and it should have not have been 938, it should have been 978. 2,350 minus 978 equals 1,372, and that's greater than 10. So both are greater than 10, so the sample is large enough to use the normal approximation. Please make sure you include that statement. Please make sure this statement is included. All right. So we have 978 divided by 2,350 is 0.4162. So p hat's 0.4162. So I wrote it in for here. I need to do a 99%. So let's do that real quickly. Second vars. And by the way, be real careful on this. I've read some notes. This is one of the places people make careless errors, and they go from a full point to getting a partial. Well, obviously, you know this stuff. So make sure you check that. Make sure you typed it in right. And so I end up getting 2.576. Then I have 0.4162. That's my p hat. 1 minus p hat over my sample size. Now I'm going to actually run the test using a calculator. So stat, test, and I have to scroll a ways to letter A, which is 1 proportion, Z interval. Press enter. X is 978. My sample size is 2,350. My confidence level is 0.99. And I get the value 38998 and then 44236. Looks like I have one too many fours. And we write our conclusion. We are 99% confident that the true population proportion of vaccine eligible people who received the vaccine lies within the interval this. If you'd done all that work correctly, you'd only got partial credit. Why? Because you didn't answer the question. It said the question was, comment on the belief that 45% of the vaccine eligible people had received the flu vaccine. Well, I look at that interval and I don't see 45%. So because 45% does not lie within the 99% confidence level, we do not believe that 45% of the vaccine eligible people in the US received the vaccine. So because 45% doesn't lie in the interval, we don't believe 45% received the vaccine. Simple. All right. And that one statement on top of the work above would get you full credit for that part.
The law on their arms seems off, so I have a feeling we're going to go to the doctor today.
Hold on just a moment.
Yeah, I know.
Suppose a similar survey will be given to vaccine eligible people in Canada by Canadian health officials. A 99% confidence interval for the proportion of people who will have the flu vaccine is to be constructed. What is the smallest sample size that can be used to guarantee that the margin of error will be less than or equal to 0.02? Well, in this particular case, Canada and the United States are different, so they probably have different proportion of people who received the vaccine, or it's reasonable to believe that. So consequently, we don't have a starting percentage to work with. So I'm going to start with, if I don't know, I have to start with the worst case scenario. And the worst case scenario is the one that gives me the biggest variance. And the biggest variance is going to be based on 0.5. So 0.5 times 1 minus 0.5. The 99% that we calculated before is still the same, so I'm not going to go back and do that work. So I divide both sides by 2.576. I square it, and ultimately I end up getting 4,147.36. Because I have anything there, I have to round up. So I round up to 4,148. If you had rounded down, you would have gone down to partial credit. So please make sure you round up on these. All right. We're moving along much more rapidly than I thought we would. An environmental science teacher at a high school with a large population of students, maybe I should reread that. An environmental science teacher, Mrs. Long, at a high school with a large population of students, Reagan, wanted to estimate the proportion of students at the high school who regularly recycle plastic bottles. The teacher selected a random sample of students at the school to survey. Yay, random sample, that's good. Each selected student went into the teacher's office one at a time and was asked to respond yes or no to the following questions. Do you regularly recycle plastic bottles? Based on the response, a 95% confidence interval with the proportion of all intervals at the school would respond yes to the question was calculated. Perfect. So they gave us this confidence interval. So how many students were in the sample? Well, first off, I write down my question or my equation. This is what I need to know. Well, I look and go, I need to know p hat. I don't know p hat. Except I know that the parameter is always directly in the middle of any interval. So in this case, I add this and I add this, and I divide by 2, and I find out that I have a p hat of 0.07. Now, another thing that I'm missing is the margin of error. Well, margin of error is how far any endpoint is from the center. So 0.7, and I could subtract, as long as I had the difference between any one of the endpoints and my center, I'd be good. So I find out that my margin of error is 0.116. A little trickier there because they didn't tell you which margin of error. You had to calculate it out. So my margin of error is 0.116. And that has a minus, that equals, and then I need my Z star, which is 1.96 because it's 95%. And we'll do real quickly do that. Second vars, inverse norm. And we get the 1.96, so that's where that came from. My margin of my p hat is 0.7, so 0.7, then 1 minus 0.7. That multiplies together to get 0.21, and I divided both sides by 1.96. Once I square it and solve, I find 59.96. So basically, Mrs. Long took a sample of 60 students. Now, the next part of this is just to spiral back some information, trying to bring back some stuff that we may have forgotten. So given that the method used by the environmental science teacher to collect responses, explain how bias may have been introduced and describe how the bias might affect the point estimate. So not only do we have to say how it was introduced, we also have to say how it's going to affect the point estimate. How is it going to affect p hat? Because students know that the environmental science teacher cares about the environment, they may feel pressured to respond yes in order to please the teacher, even if they don't actually recycle. This is an example of response bias. You didn't have to say it was response bias, but you know that if a teacher asks you a question, there's a certain amount of response bias. When I ask you guys, hey, do you all understand this? Everyone nods their head yes, even though half of you are sitting there going, no, I don't understand. So response bias is because it's either an uncomfortable question, and so you're inclined not to tell the truth, or the question is worded poorly. So that takes care of how it was introduced, but now what's the consequence? Well, as a consequence, I'm going to have too many people saying yes. Consequently, I'm going to overrepresent the population of students who recycle the bottles. All right? As a consequence, the sample proportion of students who claim to recycle would be higher than the actual population of those who do. The statistics teacher is a jerk and was concerned about the potential bias in the survey and wanted to help out this science teacher. What an awesome individual, jerk. To obtain a potentially less biased estimate of the proportion, the statistics teacher used an alternate method for collecting student responses. Took a random sample of 300 students, and each student was given the following instructions on how to respond to the question. In private, flip a coin. If it's heads, you must respond no, regardless of whether or not you recycle. So regardless of the question of recycling, if you get a heads, the answer is no. If tails, answer the question whether you recycle or not, truthfully. So that way, we don't know which question you're answering. We don't know if you're saying no, you don't recycle, or no because you got a heads. We don't have a way of knowing. That's the purpose of this. So what is the expected number of students from the sample of 300 who would required to respond no because of the coin flip? So basically, I have 300 people flipping a coin, and I expect it to be heads 50% of the time. So 300 times 0.5 is 150. So I would expect there to be 150 heads. So consequently, I would expect 150 students to respond no just because of the coin landing on heads, not for any other reason, not because they recycle or don't recycle. They're just saying no because it lands on heads. All right. Part 2 of that same. Results of the sample showed that 213 of the students responded no. So we expected 150 and 213 said no. Based on the results of the sample, give a point estimate for the proportion of all students at the high school who'd respond yes to the question. So we just said 213 responded no. We expected 150. So that means 63 said no, and we believe they said no because it landed on tails and they really don't recycle. All right, so they answered the question and they said, this is where they answered truthfully. So what's my point estimate? Well, I would expect them to land 150 times, 50 times. I would expect it to land on tails. And of those, 63 said no. So that means 150 minus 63, so 87 said yes. So of the students who had tails, who actually answered the question about the bottles, 87 said yes, so 87 over 150. So based on this sample, our estimate of the population who actually recycle is 0.58. Okay. Wow. I should have planned on going through more questions today, but obviously, I don't have them ready, so I'm not going to do it. So a survey will be conducted to examine the educational level of adult heads of households in the United States. Each respondent in the survey will be placed into one of the following 2 categories: does not have a high school diploma or has a high school diploma. The survey will be conducted using a telephone interview. Random digit dialing will be used to select a sample. For this survey, state one potential source of bias and describe how it might affect the estimate of the proportion of adult heads of households in the U.S. who do not have a high school diploma. There are numerous reasons. I'm giving 2 here, but they're numerous. Only people with phones can be selected for the survey, obviously, because they're using a phone interview. People without high school diplomas may not be able to afford a phone and assets and may be underrepresented in the survey. As a consequence, the survey will overstate the proportion of people who have a high school diploma and understate the proportion of those who do not have a high school diploma. So I said, how did bias introduced? Because people without high school diplomas may not have a phone, so they're underrepresented. That's how it's introduced. Consequence, it overstates those who have diplomas and understates those who don't. Another method, or another way, because this is a sensitive question, it is subject to response bias. A person without a high school diploma may feel embarrassed and may lie to say that they do have one. As a consequence, the survey will overstate the proportion of people who have a high school diploma and understate the proportion who do not have a high school diploma. And there's several different options on this. Just make sure that when you answer the question, you give the source of bias, why it's biased, and then you explain how it's going to impact the study. Is it going to overrepresent or underrepresent, or what is it overrepresenting and what is it underrepresenting? A pilot survey indicated that about 22% of the population of adults heads of households do not have a high school diploma. Using this information, how many respondents should be obtained if the goal of the survey is to estimate the proportion of the population who do not have a high school diploma to within 0.03, with a 0.95% confidence level. So we know something. So this we can use as a p-hat. We also have a margin of error right there. Okay? I'm not going to redo the z-star because we've done it several times, but for 95%, z-star is 1.96. And p-hat 0.22 minus, and then 1 minus that. We solve, and we end up getting 732.47. So n, I must round up, is 733, so 733 adults would needed to be surveyed. Finally, since education is largely the responsibility of each state, the agency wants to be sure that estimates are available for each state as well as for the nation. Identify a sampling method that will achieve this additional goal and briefly describe a way to select a survey sample using this method. So when I read this, they're saying, hey, I want every single state in the United States to be represented. How can I do that? Well, I can take a sample from each state and combine them all together. Well, that's called a stratified sample. So that's what I'm going to do. A stratified sample should be utilized in which each state represents a strata. That's a super important sentence. So I need to sit there and say what it is I'm going to do, a stratified sample, and then I need to identify the strata. Then I need to say how I'm going to do it. And within each state, a random survey of adults would be selected proportional to the state's population. The results from all the states would be combined to represent the United States. And that would have given you full credit. So on proportions today, what we've generally gone over is one sample proportion confidence intervals, and we did a lot of sample size. I would not be surprised if those showed up. And you can see how they brought in other material that we've talked about, from bias to surveys, et cetera, and mix those together to ask questions. I'm going to go ahead and stop the recording so that we can talk and answer questions. And then I also have some questions I'd like to ask you. So here we go.